Welcome to day 4. We're going to look at a couple special things. One is called the number E, and the other is going to deal with the word continuous growth and decay. We're going to play with this function f of x equals 1 plus the fraction 1 over x, the whole quantity raised to the x power, and we're going to put in bigger values of x and see what happens to this value. So I'm going to do this on my calculator. I'm going to show you how we can do this quickly, maybe on a calculator, by using a special fraction key. So we're going to type in parentheses 1 plus this fraction. I could do 1 slash x. I could, or 1 slash 1. I like using this. Hit alpha y equals this special key number 1. You get this nice little fraction bar. So it's going to be 1. In this case, our first number we're going to use is 1, arrow to the right, close parentheses, raised to the first. So this quantity in the denominator is 1, this quantity here is 1, and this is what we'll be changing every single time, the denominator and the exponent. Obviously that's 1 plus 1 raised to the first, which is 2. I'm going to do another one, and I'm going to cheat here a little bit. I could just go up and gather it, and hit enter. It's going to copy it over, and I could just modify. This number is 2, and this number is also 2. So one way to do it by just moving your arrows and rewriting over the number. I hit enter. I get 9/4, or if you want to make it a decimal, 2.25. Okay, because we're going to write everything as decimals up to 4 decimal places. Now when I want to do the next one, I could just capture this one above it. I'm going to change my exponent to 10. I'm going to change that denominator also to 10. And hit enter. And we get that decimal number. So I'm going to go back to the paper and I'm going to write in what we have so far. So right now we have 2, 2.25, and only using 4 decimal places, 2.5937. Back to my calculator. I'm going to do a few more while I pause the camera. So you see I did the next values for x, 100, 1,000, and 10,000, and you can see we're always getting a little bit bigger every single time. But I think we're getting, our rate of increases is less and less. I can go to my paper and write 2.7048, 2.7169 when I write it to 4 decimal places, and 2.7181 is me writing to 4 decimal places. Now I'm going to go do the last two for 100,000 and a million. And here are the last two values. I plugged in 100,000 for the x's and I plugged in a million for the x's. And you can see the numbers barely move. They're barely different. It takes 1, 2, 3, 4, 5 decimal places until we get a difference in these two numbers. Even though this was the biggest jump in x, I went from 100,000 to a million, increased by 900,000. So going to my paper, I get 2.7183 when I do it to 3 decimal places, and 2.7183 when I do it to 3 decimal places. We're going to have to make note how they are different. So you see we completed the table, and you see I noted that the two numbers, even though they're the same to 4 decimal places, there are some differences. It takes that 5th decimal place to see a difference. So let's look at the trend of the numbers. These numbers are definitely increasing. There's no doubt they're increasing. But how are they increasing? Well, I think the rate of increase is smaller and smaller all the time, so it's increasing at a decreasing rate. If we remember, increasing at a decreasing rate would be a graph that looks like this. It goes up and gets less and less. So to me, this graph is leveling off. And I can actually go see this on the calculator. Okay, I have this on the calculator. I put it in here. I typed it in. I'm going to do the graph of it. I'm going to change my window. Maybe 100 is good. I don't think I need y max to 100. I think so far we haven't really got above 3, so I'm going to make my y max equal to 3. And here's what the graph looks like. You could tell it does increase, but at some point it is leveling off to some number less than 3. Let's try to figure out what that number is. So as x gets larger and larger, where is this y value going to? It is leveling off, and it's leveling off to this very special number, 2.71828, and it kind of goes on forever. Okay, this is equal to the very special number called e. I'll show you where e is on the calculator in a minute. This is called the natural number. It was named after this guy named Euler. I know it begins with an E, and his name is not Euler, it's Euler. So this is Euler's number. And it is an irrational number. It's a decimal that goes on forever and does not have a pattern to it. So for this example, having 1 plus 1 over x raised to the x as x goes infinity, it approaches the number e. And the number e on your calculator is shown over here in a couple of spots. Okay, I could do second and hit the little division sign, and there's the number e, and there you go. The 1828, 1828 don't repeat forever. It's just those are the it just happened to be in order there. Or even better, we're going to use this key a lot. Next to the number 4 is the ln key, and above it in blue is e to the x. Why I like this key better? Because it gives me, not only does it give me e, but then it gives me e raised to an exponent. We're going to use that exponent a lot today. So I would just do e to the first, and there we go, we get the number e. So in this paragraph, it talks about how e happens all over the place for whether we're doing compounded interest or a bell curve or many different ways that we do. But we're going to use it, these two formulas. I don't care if you use raised to the Rx or raised to the RTA. I don't care what you use for your input. But we use this when we hear the word continuous and exponential. So if something is continuous, you hear the special word continuous. That's the key. Not regular exponential, continuous exponential. So then we have this R in here. Okay, R is just the rate, just like we had before. So we have positive R's and we have negative R's. Positive R's are for continuous growth, and negative R's are for continuous decay. If you think about it, e to the 0 is equal to 1, because anything to the 0 is equal to 1. Well, e to a positive, which is bigger than 0, is going to be something bigger than 1. And e to a negative, negative exponents don't make negative numbers, they just make 1 over, is going to be something smaller than 1. So that's what we're going to use. We're going to use a positive rate for continuous growth and a negative rate for continuous decay. So for my two examples here, I have a village with a population of 1,000 growing continuously, that's the key, at this rate. Well, a 0.5% is the number 0.005 when you change it to a decimal. So my population of this village is going to be 1,000 e raised to the 0.005 t. Now, here's the thing I should have wrote. Do not do 1 plus or minus r when we do these rates. We don't have to add 1 to that for growth. This e already kind of has that 1 in there because e to the 0 is already 1. We don't have to add it to it. Okay, that's the big difference. And now we have a population starting at p sub 0, which is fine, just some population shrinking or decaying at this rate. Well, this rate would be 0.0312, but since it's shrinking, I'm going to use a negative. So this population is equal to p sub 0, e to the negative 0.0312 t, and these are this model that we're going to use. Again, for these r values that we used as the exponent, Do not add or subtract from 1 because we just use what we see. Growth means positive, decay means negative. So as we did yesterday we worked with the form a times b raised to the t over k, and we changed it to the regular form a times b to the x. Well, we're going to do the same thing here. So I need to change e to the rt into b to the t. I'm going to use the same method. I'm just going to use t equals 1. So that means I just do e to the r times 1, or e to the r becomes my new b. Okay, that's what we're looking at. And it's a really easy process. You just have to use your calculator. So looking at this problem right here, I'm going to move these up a little bit. I have the very first problem. I look at this, and I'm like, well, is it growth or decay? It's definitely growth. How do I know it's growth? My R value is positive. What's this continuous rate at? Well, 0.25 means it's growing continuously at 25%. So now I have to convert this. The way I convert this, I do e to the 0.25, and I'm going to go to my calculator to do that. So when I go to my calculator, I really like using this second ln key, or what above it is in blue is the e to the x, and just typing in e raised to the 0.25. And notice, since that's a positive number, it is bigger than 1, and I'm going to use that as my b value. So now my new equation is going to be q of x is still the initial value of 0.3, but inside the parentheses is 1.284 raised to the x. Well, that's still growth. Why? Because the b value is bigger than 1. And now I'm going to do 1.284 minus 1, which is 0.284, and that's 28.4%. So here's the idea. Continuous growth by 25% is a regular growth of 28.4%. Continuous growth means that it's happening all the time. You know, not every minute, not every second, faster than that. And regular just means like one duration, like once per year, or whatever you set your time frame to be. So this next problem, I look at this, I'm like, oh, I have an R rate that's negative, so this must be decay, because my R is negative. Well, I see that R rate is negative 0.10, so that means it's negative 10%. You want to put negative in front of it, go right ahead, it won't bother me because it is decaying. Figure out to convert it, I have to do e to the negative 0.10, and this is where I go to my calculator. I go to the calculator and type in e raised to the negative 0.10, that R value, and I get this value here that I'm going to use as my b. Equals 0.905. I like running to 3 decimal places. So now I have R of x is equal to, still the initial value of 5, 1, excuse me, not 1, wasn't paying attention, 0.905 raised to the x. This is still decay. How can I tell it's decay? Because that b value is less than 1. So I just do 0.905 minus 1, I get negative 0.095. It's negative because it's decay. So my decay rate would be, if you want to put a negative, but it's just 9.5%. The negative just reinforces that it's decay. So a continuous decay by 10% is the same as a regular decay by 9.5%. For this last one, I see this number here is bigger, it's a positive number, so this is definitely growth because I have a R value that is positive. That R value that I see here is 1.5, and 1.5 times 100 means I have 150% continuous growth. That's a lot. I'm going to convert this in my calculator. I'm going to do e to the 1.5 on my calculator to figure out what that value really is. And I hit the blue second, I hit the ln key to get the e with an exponent to the 1.5. I get this big number, it's a lot bigger than 1.5. I'm going to put that on a piece of paper. E to the 1.5 was 4.482. So now I can rewrite this as s of x is equal to 3, the initial amount, 4.482 raised to the x. Definitely still growth, because that b value inside the parentheses is really bigger than 1. So 4.482 minus 1 is 3.482 times 100 is 348.2%. So a continuous growth of 150% is the same as a regular growth by almost 350%. That continuous really adds up when you look at those bigger percents. Okay, let's write some models. Country C, population of 2, growing continuously. Remember that word continuously is the big thing. And 1.5% is 0.015. So I get C of x is equal to 2,000 e to the 0.015 x. I do not need to add a 1 to that because it is growing. That e basically keeps a 1 in there. On country D, population 10 decaying continuously at 2.6. So I'm going to use, that would be 0.026, but it's decaying. I'm going to make it a negative. So country D is equal to 10,000 e to the negative 0.026 x. Those are my two equations. Then I ask one of these two countries going to be equal. So I'm going to go to my calculator in a minute. I'm going to put y1 as 2,000 e to the, be nice if I write correctly, 0.015x. y2 will equal 10,000 e to the negative 0.026x. And off my head, I know the graphs are going to look like this. y1 is going to start at 2,000 and grow. y2 is going to start at 10,000 and decay. So again, I'm trying to find their intersection. So I'm going to put this in the calculator. I'll actually type this in the calculator on screen. 2,000. Second, that E key, 0.015. The X keys are in the mode. And 10,000. Second, that E key, negative 0.026. X, don't forget your X, you need a variable. And now I should pick a good window. What would be a good window for this? Remember, X stands for year, so this would be 0 to 100 years. Maybe that's a good thing. I'm going to keep it. Now, my Y max of 3 is not going to work. I know that's not even close. I know the one starts at 2,000 and goes up, the other one starts at 10,000 and goes down. I'm going to make it 10,000. I might as well see both exponential. If 10,000 is too high, I can adjust it later. I hit graph, there's the growth, there's the decay, and look, they do hit kind of towards the middle. Second, trace, number 5, enter, enter, enter. And I get they intersect. Make sure you get this intersection at the bottom. You haven't done it correctly, you don't see the word intersection. At about almost 40 years. So according to my model, they intersect at x is equal to 39.255 years. Okay, almost 40 years. So I want to know how many years it takes for the population of C to surpass 8,000. I'm going to keep y1 in my calculator, but instead of getting rid of y2, I'm going to make a new equation. y3 is equal to 8,000, because I could just turn off the y2 equation and see where they intersect. I know from what we've done for the last few days, here's my y1, the growth, here's my y3, the horizontal line 8,000, and let's see where they intersect by going to the calculator. So here I am on my calculator with my two equations, and I want to keep my y1 going, but the y2 I do not want to graph, so I'm going to move the cursor over to equal sign, hit enter, and now when the equal sign isn't bold, it's not going to graph. But I do want this one to be 8,000. And you know what? I think I'm going to keep the same window. Probably not too bad. Barely gets in there, but they do intersect. Second trace, number 5, enter, enter, enter. And you see it takes almost a little bit more than 92 years for country C to get to 8,000 people. So this intersection is x equals 92.420 years. That's that one. And this last one, now I want country D below 5,000. So I'm going to use that Y2 equations. That's why I didn't get rid of it. I realize I might want to use it later. And I'll make a new equation called Y4 equal to 5,000. And we'll see where they intersect. Like I said, I know that Y2 is decay. Y4 is this horizontal line. I want to see where they intersect. So I'll go to the calculator to see where they intersect. So here I am at my calculator, my Y1 equation. I don't really need my Y1. I'm going to turn it off. My Y2, I do want on now. I'm going to bold it. Y3, I don't want at all. I'm going to turn it off, and then I'm going to put Y4 as 5,000. And I'm going to use the same window, so I'm going to just hit the word graph. And there are those two curves, the decay and the horizontal line of 5,000. Second trace, number 5. And a little bit less than 27 years is where these two graphs intersect. So I get x is equal to, let me put the pink back up, x is equal to 26.660 years is where they intersect. And there we go. That's how we do it, using our graphing calculator and using this new model. We've talked about 3 models now of exponential functions. We have y equals ab to the x, the regular form, y equals a times b raised to the t over k, when we have half-life and doubling time and things like that, and then y equals a times e to the rx when we have continuous growth or decay.